Hello everyone. Previously we had discussed on the topic try, right? So today we'll be discussing on the topic segment tree, right? Let's get into the definition part first. So what does the definition part say here? A segment tree is a binary tree, right? So we have already discussed on the binary tree. You have to know what binary tree is, right? So a segment tree is the binary tree used for answering range queries, like whether it may be sum, min, max, etc. Right? So a segment tree is a binary tree used for answering range queries efficiently while allowing updates on logarithmic time. While allowing updates on logarithmic time. So this part is very important. Usually we make use of the segment tree for the optimization purpose itself. Whenever there is complete optimization is required, then we'll be going with the segment tree, right? Just remember this one. A segment tree is a binary tree used for answering range queries efficiently while allowing updates on logarithmic time. It divides the array into segments. What it does, it divides the array into segments, stores result for each segment, right? It stores the results for each segment and merges them for queries Both building and querying takes big of log n. Just remember this. Both building and querying takes big of logarithmic n. We can go with the update as well in the segment tree, but usually when update is strictly required, we will be going with the Fenwick tree, right? So we will be preferring Fenwick tree. So let's see this one with a very simple example, right? So let's go with the segment tree for the range sum queries, right? So I'll just go with class. Let me go with segment tree here. This is fine. First, let's go with the initialization part. Just go with def init. Let me remove this one. I also need this one. What do we call? Array one. So I'll just consider array here. This is fine. Now, within the initialization part, first let's go with the length of the input array, right? So I'll just go with self.n. Let me initialize this one to the length of the array. This is fine. Next, we have to consider the segment tree array as well, right? Also, we have to consider the this one build. First, let's go with the segment tree array. I'll just give yourself dot tree here. This one, let me initialize this one to 0, right? This one 0 into, so basically I'll just go with 4 into self dot n. 4 into self dot n. N is nothing but the length of the array, right? So we are just going with a 4 into array in simple terms. This is nothing but the segment tree array. And also we have to go with a build, right? So I'll just go with self dot build. Let me initialize this one to self dot build of. So these things we have to consider. One is array, another one is this one, another one is 0, and another one is self dot n minus 1. So this is fine. We are done with the initialization part. Next, let's do one thing. We have made use of the build here already, right? So I shouldn't have I should have written the build method first, then I would have made use of the build here. So let's do one thing. Let's write the build method here, right? So yeah, now usually within the segment tree we will be going with the two methods, build and this one query, right? So we have discussed this one, and in the definition part as well I said this one, right? It divides the array into segment, stores the results for each segment and merges them for queries. So we have to go with a query. First we have to build the segment tree, then we have to go with a, we have to merge them, right? So we have to store the result for each segment and finally we have to merge them for the queries, right? So for that purpose we need another method called query, right? So both building and querying takes big of logarithmic n times they have given. So here let's go with the build method. Let's see first. I'll just go with the self. This one will be array, this one will be node left comma right. So this is fine. Now within the build method, first thing we have to do is we have to consider the leaf node man. If L equals R, then I'll just go with self dot tree here. So this one of node, let me assign this one to the iterated value of array, right? So not the iterated value, sorry, left, right. So there is no iteration here, sorry. So this is fine, L. So Else what we need to do, else I'll just go with, so let me give colon here, let me write it in the next line. So we have to find the middle, we have to find the middle. So for finding the middle, I'll just go with mid equals left plus right by 2. This is fine. Left plus right by 2. Next, after finding the middle within the build, we have to build the left child and we have to build the right child. So just now in the Java, we have finished the segment tree, Fenwick tree, as well as sparse table part. Right, so we have solved n number of problems. This one almost 15 problems to be exact, right? And also we have solved 10 problems in the this one JavaScript as well. By this time, we have already solved n number of problems in the contest. Whether it may be lead code, whether it may be code forces, whether it may be code chef, whether it may be at coder, we have solved n number of problems. By this time, we have to know the segment tree and Fenwick tree. Even though I'm explaining this one in the Python, just for the syntax purpose, right? I just wanted to know, right? So let's move forward. So mid here, left plus right by 2, right? So we have to find the middle, and then we have to build the left and right child, right? Finally, we have to build the left and right child, and then we have to merge. These three things are left. First, let's build the left child. For building the left child, I'll just go with self dot uh, build. So this one will be array comma 2 into node, right? Along with it, left and right. We have to consider left and, sorry, we are building the left, right? We are building the left child. Basically, we'll be going with this left and mid only. So let me copy the same thing, and let me paste it over here. This one remains same, self dot build for the right child, and array 2 into node, this one remains same as well. But in this case, we are moving from left to right, right? So we are building the right, this one, what do we call, right child. So this remains this one, node plus 1. Instead of L, this will be mid plus 1, and here I'll just give R, right? Right, so we are done with building the right child as well. Now all we are left with is we have to merge. For merging, I'll just go with self dot tree of node. Let me assign this one to the self dot tree 2 into node. This is fine. uh Let me go with 2 into node. This is also fine. Plus self, again self dot tree, we are merging this one 2 into node, and this one, left and right, basically 2 into node plus self dot tree of 2 into node plus 1, right? So self dot tree of, so this one I would have copy pasted the same thing and made the necessary changes. We just have to go with plus 1, right, for the right child. So this 18, line number 18 is nothing but we are building the left child. Line number 19 is but nothing but we are building the right child. So line number 20 is nothing but we are merging both left and right subchild after building, right? So this one is for this one. We have to find the middle, right? So this line number 14 and 15 is nothing but we are considering the leaf node. We are considering the leaf node. This is nothing but the initialization part. We have already discussed this one, right? So we are done with the this one, what do we call, build. We are done with the build part. Next, let's go with the query. Query is simple, right? So I'll just go with def. Let me go with a query here. All I need is self node l comma r, and also we need q1 and q2, query 1 and query 2. So this one I'll just go with a q1 and q2, right? So this is fine. Now within the query method, let's do one thing. First we have to consider three things we have to consider within the query. Just remember this one. Every problem will be going with the same thing. First we have to go with the no overlap, then total overlap, then the partial overlap. These three things will be considering. Remember, every time whenever we are going with a segment tree, so whenever we are going with a build, right? So first step is we will be going with the leaf node, and then we will be going with the finding the middle element, and then we'll be going with building the left and right child. Afterwards we'll be merging. This is simple build. And one more thing, we will be going with a one more method, as I've said, query as well, right? So usually we can go with the update as well within the segment tree, but usually whenever there is updation required, right, usually, so it's better to go with the Fenwick tree. right? So let's discuss the build and query. Build and query both request big of logarithmic end time, right? So usually we will be solving the problem where build and query is required, right? So just remember this one, right? Now mm, when there is no overlap, right? So I'll just go with overlapping intervals. I won't say intervals, basically query 1 comma 2 1 comma 3, that range will be given, right? That we have to consider. When there is no overlap means query, when there is, it is less than L or QL greater than R, then what we need to do here, so we have to return 0 in that case. So we have to return 0 in that case. And the next step is when there is total overlap, complete overlap, right? So then we can write in this way, QL less than or equal to L, and write less than or equal to this one, QR, right? So then query, QR itself I have considered, right? So just give me, oh, sorry, man. This one I have considered Q1 and Q2 query. This is not query 1 and query 2. I got confused, I think. So this one is query left and query right. Sorry, sorry. Yeah, this is fine. Still we haven't made use of the node anywhere, right? So this is fine, man. QL and QR. Sorry for this. And now let me return something here. Hmm, what we need to return? We are going with a total overlap, right? So this one will be self dot tree of node, right? So this is when total overlap, this is for the total overlap, sorry. Next, what we need to do, we have to consider the partial overlap as well, right? So for the partial overlap we have to calculate the mid, right? So mid equals left plus right by 2, simple. Then let's go with the left sum, then right sum, and finally we have to this one, sum up left sum and right sum, these two things, right? So when there is partial overlap, so we have already written the recursive. Let's go with the recursion here. Left sum equals self dot, let's make use of the query here, sorry, what did I paste here? So this one will be query, let me type this instead. So this one will be 2 into node comma left comma mid, this one has to be QL comma QR. So this is fine. Now let's go with the right sum. This one will be right underscore sum. This one will be self dot query. This is fine. This one will be 2 into uh, this will be node, sorry, as we are considering we have to go from left to right, this one is right, right? So this one will be node plus 1, also mid plus 1. While building we have discussed this one, the same thing, right? So while building the left and right child, so we are going with the right child, mid plus 1. Then we have to consider right. So this one will be right along with the this one QL and QR. So this is fine, we are done with this almost. So finally we have to return the sum, right? So I'll just go with left sum plus right sum, right? So we are done with the code. So this is it for the basically this is it for the segment, this one segment tree, right? So a simple segment tree class initialization part. So we saw the build process and also we saw the querying process as well, right? Very simple. Now let's test, or let's go with the example usage, man. Simple one. I'll just go with array equals 1 comma 3. I'll just take some random, this one 135, just the odd numbers here, 7 9 11. This is fine. Now let's go with a segment tree. Nothing but I'll just consider snt here, this one st of segment tree. Let me pass the array here, this is fine. Now let's do one thing, let me print something here. Print of segment tree, nothing but st dot query, this is fine. So this one will be 1 comma 0. We have to consider length of the array as well. I'll just go with a len of array. So let me go with minus 1, 1 comma 3. So I have just given, this is not the random numbers. So this is just that we are querying the sum from index 1 to 3. See here, we are querying the sum from index 1 to 3, right? Length of the array we are considering first, because this one length of the array 1 2 3 4 5 6, right? So length of the array we are querying from the sum 1 to 3, we are starting from 1 basically, right? So this is fine. 1 to 3, that's what we are doing. We are querying the sum from index 1 to index 3, right? So just keep this in mind. Just give me a second here. Yeah, uh 1 second. Yep. So the final output that we need to get here is 15, right? So the final output that we need to get here is 15. 15 means we are just summing up here, right? From 1 to 3. So index 1 to 3. So this one you can just go for 7 plus 5. That is nothing but 12. 12 plus 3 is nothing but 15. We are just querying up from this one. Querying sum from index 1 to index 3. Querying what? Querying sum. So we can just make use of the sum. See here, sum. We can just go for the min. We can just go for the max and other purposes as well, right? So in the example, see, I have said again. Let me go with the definition here. The segment tree is a binary tree used for binary tree in the sense it can have at most two nodes, right? A segment tree is a binary tree again, right? It can have at most two nodes used for answering range queries like whether it may be sum, min, max, right, efficiently while allowing updates on logarithmic time. See here, we are going for the sum basically in for this particular example. So we are going from querying the sum from this one index 1 to index 3, right? So this one, when we sum up 7 plus 5 is 12, 12 plus 3 is 15. We have to get the output 15 because see here, 1 to 3 we are giving here. This is fine. Let me run the code. We have already written the query. I have explained build and query methods as well. So I'll just go with Python here. So this one, let me come here. Let me copy the file name, paste it, .py, right? See here, we are getting the output 15. Simple. So we are done with the segment tree part, right? So we have got the sum from index 1 to 3, nothing but 3 plus 5 plus 7 in this case, right? So this one 3 plus 5 plus 7, right? So that is equivalent to 15. So I hope the segment tree part is completely clear, man. Simple, easy, right? So now let me summarize whatever we have learned so far. So segment tree allow fast range queries and update. Basically we will be getting the solution in logarithmic time, right? So see here again, efficiently allowing updates in logarithmic time. So this is purely used for the optimization purpose, right? So efficiently while allowing the updates in logarithmic time. So this is the reason I said you this is very important. Remember this one, right? A segment tree is a binary tree. It can consist of at most two nodes used for uh, this one answering range queries, whether it may be sum, min, max, efficiently while allowing updates in logarithmic time. Very important, right? So next, it divides the array into segments. Yes, it does. Stores the result for each segment. Yes, it does. And merges them for queries. That is the reason we have made use of the query method. And for the build, we have made use of the, we have to build the segment tree first. Yeah, right? So again, build this one query because we have to merge them for the queries, right? For first we will store the this one results for each segment, then we have to merge them for the queries. So that is the reason I have written this one query method here. Both building and querying takes big of logarithmic n times, right? So that's what, just keep this in mind. And let me summarize again whatever we have learned so far. So just keep this one sentence in the mind. Segment trees allow, what does it allow? Fast range queries and updates, making them essential for this one, competitive programming problems involving intervals basically. That's what I said, right? So again, segment trees allow fast range queries and updates, making them essential for competitive programming problems involving intervals, right? So we are done with the segment tree part. Next we'll be discussing on the topic Fenwick tree or the BIT, nothing but binary index tree. For now, this is it. Thanks for watching, guys.